Here's a question for you. Is it possible to start at the blue point, visit every red point exactly once, and get back to the blue point in less than 20 miles? This problem, known as the traveling salesman problem or TSP, is surprisingly difficult. In fact, we don't know of any efficient methods to solve it. What's interesting though is that any potential solution to a given instance of the TSP can be checked very quickly. All we have to do is find the total length of the proposed path and check if it's less than the maximum allowed distance. Questions like these form the basis of the P versus NP problem, which is considered by many to be the most important unsolved problem in computer science. Here, P and NP are called complexity classes. Specifically, P refers to decision problems, problems that have a yes or no answer, that can be solved in polynomial time, whereas NP refers to decision problems for which a solution can be checked in polynomial time. For our purposes, you can think of a polynomial time algorithm as a fast algorithm. The statement of the P versus NP problem is very simple. It asks, does P equal NP? Clearly, every problem in P is also in NP. If we can solve a problem quickly, we can check its solution quickly as well. So in other words, P versus NP asks, are there any problems here that can be checked quickly but not solved quickly? We've already seen that TSP is in NP because we can check any potential solution quickly. What's interesting is that the TSP is one of the hardest problems in NP. How do we know this? Well, one way to think about the relative difficulty of problems is in the context of reductions. We say problem A reduces to problem B if we can reframe the problem in a way such that solving B gives us the solution for A. Every NP problem reduces to the TSP, which means TSP is at least as difficult as every problem in NP. The set of problems that satisfies this criterion is known as NP-complete. In fact, every NP-complete problem is just as hard as every other NP-complete problem. If we could find a polynomial time algorithm for one, we could find a polynomial time algorithm for all of them, implying P equals NP-complete. So why should we care? Here's one reason. Most encryption systems rely on the assumption that P is not equal to NP by making use of one-way functions that can scramble data in a way that's very hard to reverse. A proof that P equals NP would imply that these functions can't exist, a breakthrough that could change the future of cybersecurity forever.